All right, so number 9 on this sheet, we are trying to open a barn door. So it says a large barn door is a solid rectangle made of wood. So that right there is important information because it's steering us in the direction of picking one of these guys, right? So did you figure out which one to use, Sam?
For the solid rectangle,
Yeah.
maybe 1/3 MR.
Yeah, which one are you looking at? They're all 1/3 MR squared, but what's important is you got to figure out how to measure your R.
Oh, the one on the last one?
The last one, this one, right? You guys see that? Because a barn door is going to pivot like this around one end, right? Not around the middle. The one above it is pivoting around the middle, right? So we don't want this, we want this. All right? Notice it gives you the width of the door, and frustratingly, this sheet has this dimension listed as width, which is weird to me, right? Like to me, this would be the width. So, do you guys see that? All right? So, this, for our barn door in number 9, it says it's 0.8 meters wide. So for us, R is going to be 0.8 meters. Clear? All right, so here we go then. So we've got a large barn door. I is 1/3 of MR squared. The problem gave us both of those values. It told us that the mass is 30 kilograms, and it told us that the radius is, what did I just say, 0.8 meters. So plugging those numbers in, you can calculate your I, and it turns out to be 6.4. What are the units on I, you guys?
Kilogram meters squared.
Good. Kilograms for M times meters squared for radius. All right. Is everybody good up to there? We're good? Ray, you good? What are you doing?
What?
All right. Everybody good? Okay. I just couldn't figure out who you were whispering at. It looked to me like.
Nothing worse than the song.
Oh, is that what you were doing? All right. All right. All right. It says the door is swung with a constant acceleration from rest. Swung from rest through an angle of 75 degrees. What should I do with that 75 degrees, you guys? Convert it to radians, right? So that's going to be my delta theta. When you convert it, it gives you, is it 2.09 radians? Is that right? You guys are useless. I'm angry at you all. 75 times pi divided by 180. No, Mr. Hecker, that's not right. I got 1.31. Oh, thanks for your help. I'm giving you a steely look, and you didn't even care. I'm mad at you. All right, everybody good with our delta theta? All right. Okay, and this all takes place in a time of 1.8 seconds. All right, now the question wants to know how much force is needed. So we're looking for the force again. So this is actually very similar to the one I was just talking about a minute ago with Tim, but the calculations I think are a little trickier. All right, so again, FD equals I alpha. We're looking for a force, right? So to find the force, we need to know the torque. To find the torque, I got to find I and alpha. I already know I. Now I got to find alpha. Do we see a way that we can use some of this information here to find our alpha? Sure, go ahead and get us started. Tim.
Can you take your angular displacement, multiply it by your radius, so you have your so you have your linear acceleration, and be able to find you have your linear displacement to find linear acceleration, and that way you just multiply it by the mass and the force.
Oh, I gotcha. I'm super glad you said this. So what you're saying is I can use a jumper to find my displacement and find the linear acceleration, right? And then just do F equals ma. Super, super common issue. You can't do that. Newton's second law does not apply to these problems. Okay? Because the door is not, or the problem is not about a door that's accelerating. The door is rotating. If the whole door was accelerating, then we could do that. But that's not the case. All right? Anytime, I'm glad you said this. This was a big problem that I didn't realize was a problem until I gave the test last year. You can't use F equals ma when you're talking about a thing rotating. because the whole object doesn't have the same acceleration, right? The outer point is going to have a bigger acceleration than the inner points, right? So F equals ma is a big no-no here. Follow? Okay? So, for the purposes of this chapter, if you're looking for force, really, this is your only tool. Follow? Good? Sorry, I didn't mean to, I hope I wasn't really harsh there, but I want to make sure you get it, because it's big. Clear? Okay, cool. Abby, what do you got? You had a hand up.
Oh, I was just saying, so could you just use one of the equations on the sheet to find your angular acceleration?
To find the angular acceleration, yeah. So, Tim, I think you were headed down the right path. I think you just were thinking linear instead of angular. So I think the idea is, and what Abby is getting at, do you know which equation works, Abby?
Yeah, it's the delta theta equals 1/2 alpha t squared
There you go.
plus w by t.
So, in other words, just find the angular acceleration instead of the linear. Cool? All right, everybody good? Tim, you good?
Yep.
Cool. All right, I will leave you alone now. All right, so 1.31 equals 1/2 alpha, which is what we're looking for. Our time is 1.8. Don't forget to square it. Omega I is 0. And solve for alpha. So, if you do this, your alpha turns out to be something. Oh, it's 0.808. Radians per second squared. Good? Any problems? All right, so now that I know my angular acceleration, why do we care? I said, why do we care? Yeah, now we can find our torque, right? And once we know our torque, we can find our force. So here we go. Net torque is I times alpha, which is 6.4 times 0.808, which gives you, it's like 5.12 or something like that, isn't it? Is that right? 0.4 times 0.808. Oh, shoot. Mm. 0.518. Or 517, sorry. Newton meters. Everybody cool up to there? All right, so now we are almost done because we can just do our one last step. Net torque is I alpha. We just, no, try again. We already did that. We got to use the other one. Net torque is FD. So our net torque we just found, it's 5.17 Newton meters. That's got to equal F times, if you're trying to open or close a barn door, where are you going to push it? At the outer edge. So your D is equal to your radius, which was 0.8 meters again. And then divide, and your force, it actually, if you round, it actually comes out closer to 6.5 newtons. I think the answer might say 6.4. Cool, you guys? Any problems with that one? Okay, cool. And then B says find the final angular velocity. So to do B, that's just omega F is omega I plus alpha T. Just plug in your numbers. Cool? Questions, issues, concerns, anything? Okie dokie.